morning, students. Today we will discuss about the topic friction. In friction we will study about the force required to move the body on a horizontal surface, then the force required to move the body when the force is applied at an angle theta to the horizontal plane, then the force required to pull the body on an inclined surface. So, this can be of three cases. The force on the body can be applied either horizontal to the plane or at an angle theta to the plane, horizontal plane, or it can also be applied horizontal to the ground. These are the three cases. And how much force is required, we can derive the expressions. We can also solve some examples for the inclined surface. Now we will come to the concept equilibrium of a body on a horizontal plane. If the body is resting on a horizontal plane, several forces are acting on the body. Normal reaction is R, which is always perpendicular to the surface of the ground, and weight of the body is always perpendicular to the ground. And if you try to apply the force P, that is pulling force, to move the body towards rightward direction, there is going to be a frictional force with the red triangle which is in the opposite direction. So mu is coefficient of friction between the body and the surface. P is the force required to pull the body. The first case, force is applied horizontal to the surface. So the force required to move the body P is equal to F. If you apply this force equal to the friction, then the body will move. But we know that F is equal to mu R, and also we know that the vertical component R is equal to W. So we can say P is equal to mu W. So if you multiply the load with coefficient of friction, that force is enough to move the body. In the first case, we have seen the force is applied horizontal to the plane. Now in the second case, we will see the force is applied at an angle theta to the horizontal plane to move the body in the forward direction. Now this force P has got two components. One is P cos theta, that is horizontal to the plane. Other one is P sin theta, that is vertical to the plane. Now we will resolve all the forces horizontally as well as vertically to solve the problem. Now resolving all the forces vertically, we have the vertical downward force is W is equal to the upward forces R plus P sin theta. So similarly, resolving all the forces horizontally, that is we have horizontal forces F in the leftward direction, and in the rightward direction we have only P cos theta. Therefore, for the equilibrium condition, the horizontal forces should be same, that means both should be equal. Therefore, P cos theta is equal to F. We also know that F is equal to mu R, and from this equation we can write R is equal to W minus P sin theta. From equation 1, P cos theta is equal to, instead of F I can write mu R. Therefore, P cos theta is equal to mu into R means W minus P sin theta, multiplying mu W minus mu P sin theta. And now bringing this minus mu P sin theta leftwards, I will get P cos theta plus mu P sin theta is equal to mu W. So taking P outside, P into cos theta plus mu sin theta is equal to mu W. From this equation I can write P is equal to, that is tan phi into W divided by cos theta tan phi into sin theta. This tan phi is because we know that mu is equal to tan phi. Instead of mu I am writing tan phi here. So, in this equation, multiplying numerator and denominator by cos phi, I am getting this one, because tan phi is equal to sin phi divided by cos phi. If I multiply with cos phi, here cos phi gets cancelled, I get w sin phi divided by denominator also I am multiplying with cos phi, therefore cos theta into cos phi plus I will get sin theta sin phi, because cos phi gets cancelled. So, I will get this one. From this I can say w sin phi divided by, instead of this one I can write cos theta minus phi. So, this is the formula, and here this p is minimum when this theta minus phi becomes 0, because cos 0 is equal to 1. So, therefore, for this condition, when theta minus phi is equal to 0, I can say theta is equal to phi. So, for the least force P is equal to w sin phi, because theta is equal to phi is the condition. Therefore, P is equal to w sin phi is the minimum force required to pull the body in the rightward direction. Okay, let us start one example. So, here is an example. A body is weighing 500 Newton is pushed by a force of 120 Newton on a rough horizontal plane. If the line of action of push is 20 degree with horizontal, find the coefficient of friction. This problem we can solve by two methods, and let us have a simple diagram for this. There is a pushing force of 120 Newton on the body. A body is weighing 500 Newton, and if the body is moving in the leftward direction, there is going to be a friction in the opposite direction. Now, for the equilibrium of the body, let us resolve all the forces vertically. The vertical force, upward force, that is R, is equal to downward force W plus P sin 20, that is also acting downward. So, we have an equation. Substituting the values, W is 500 and P is 120 and theta is 20 degree, this angle is 20 degree. So, we will get R as 541.04 Newton. Again, for the equilibrium condition, resolving all the forces horizontally, we have F, which is acting in the rightward, is equal to the other force, that is P cos 20, which is acting in the leftward direction, both are equal. Therefore, F is equal to P cos 20. Substituting, we get 112.76 Newton. So, we know that F is equal to mu r, mu is equal to F by r. Substituting the value of F, the value of r, we get mu is equal to 0.2. We can also solve the same problem by using directly through a formula. P is equal to mu w by cos theta minus mu sin theta. Here the sign is minus because P is a pushing force here. P is pushing force, therefore the sign is minus. So, P is equal to 120, W is equal to 500, theta is 20 degree. Substituting the values, we get like this, and we have cos 20 as 0.939 minus sin 20 as 0.342 mu is equal to 4.166 into this mu, it is cross multiplied. Finally, we get mu is equal to 0.208. So, both are almost same. So, you can solve either way. Equilibrium of a body on rough inclined plane. So, this is the plane surface and this is the inclined surface, and this there is a body. And now we have several cases to study now. So, here a force can be applied horizontal to the plane or horizontal to the ground, or a force can also be applied at an angle theta to the horizontal plane. These are all the several cases we will study one by one. Suppose in this case, if this alpha is more than the angle of repose, then external force is required to maintain equilibrium, because we know that at angle of repose the body starts moving down, equilibrium cannot be maintained, therefore external force is required. Now, as a case 1, force P is applied parallel to the plane and body is tends to move down. So, when body is tending to move down, the frictional force will act in the opposite direction, therefore, F is in this direction. So, for the equilibrium condition of the body on inclined plane, so resolving all the forces normal to the plane, we have R is acting normally upwards and downwards W cos alpha is acting. Resolving the W, we have W cos alpha. So, R is equal to W cos alpha. Similarly, resolving all the forces along the plane, we have P is equal to W sin alpha minus F, we can write. Instead of F, I can write mu R. So, P is equal to W sin alpha minus mu R. Instead of R, I can write W cos alpha. So, therefore, P is equal to W sin alpha minus, instead of mu, I can write tan phi, because we have the formula, into W cos alpha. So, instead of tan phi, I can write sin phi by cos phi. Taking cos phi as LCM, it becomes W, I will take it outside, sin alpha into cos phi minus sin phi into cos alpha whole divided by cos phi. This using the formula sin alpha minus phi divided by cos phi. So, this is the formula for the force required to move the body in the upward direction. So, when the body is tending to move down, this is the formula. In this case, now the force is parallel to the plane and the body is being at the point of sliding up the plane. So, when the force is applied, the body is moving upwards, therefore, the frictional force is acting in the opposite direction, that is like this. So, again for equilibrium condition, resolving all the forces normal to the plane, we have R is acting upwards, R is equal to the downward force is equal to W cos alpha, equation number 1. Resolving all the forces along the plane, we have P in the rightward direction, P is equal to, in the leftward direction we have F as well as W sin alpha. Therefore, P is equal to W sin alpha plus F. Instead of F, I can write mu R, that is equation number 2. From 1 and 2, I can write like this, P is equal to W sin alpha plus mu into, instead of R, I can write W cos alpha. We also know that mu is equal to tan phi. Tan phi means sin phi by cos phi. I can write like this, again cross multiplying, taking LCM and taking W common outside, and I get sin alpha cos phi plus cos alpha sin phi. So, using the formula, that is sin alpha plus phi divided by cos phi. So, P, that is the force required to move the body in the upward direction, this is the force, that is W into sin alpha plus phi divided by cos phi, where W is equal to weight of the body and alpha is the angle of inclination and phi is the angle of friction. In the earlier case, we have seen that force is parallel to the plane. Now, here we will see force is parallel to the base. So, this is our base and the body is tending to slide down. When the body is tending to slide down, the frictional force will be acting in the opposite direction. Now, for the equilibrium condition of the body, resolving all the forces normal to the plane, we have normal force R in the upward direction. In the downward direction, we have P sin alpha and W cos alpha. These two forces are acting downwards. Therefore, this is the equation, W cos alpha plus P sin alpha, equation number 1. Similarly, resolving the forces along the plane, we have forces P cos alpha which is acting in the rightward direction, and in the leftward direction we have W sin alpha, and F is also acting in the rightward direction. So, this P cos alpha, F,